In this video, we look at a particle in a one-dimensional leaky box and examine the energies and wave functions of its stationary states. Such a box looks like this. It has an infinitely high potential energy on the left, zero potential energy in the box that extends from 0 to A, and a finite barrier of value V0 on the right. We have three regions, and the potential energy function is piecewise constant in these regions. Now let's focus on the bound states of the particles. That is, states where the particle is trapped in a box. For such states, the particle energy E is smaller than the potential energy barrier V0. For the bound states, we have obtained expressions for the wave functions in the three regions. On the left, the wave function psi of x is 0, since the potential energy is infinite. In the center, the wave function is oscillating. Psi of x equals a times sine of kcx, where kc is a constant given by the square root of 2me divided by h bar. On the right, finally, the wave function is a decaying exponential. Psi of x equals v times e to the negative uppercase kr times x, where uppercase kr is given by the square root of 2m times v0 minus e, all divided by h bar. We also have an implicit expression for the energy eigenvalues, which is given by a negative tangent of the square root of 2me over h bar times a equals to the square root of e divided by the square root of v0 minus e. We can't solve this for e explicitly. We would need a computer and use numerical methods. We can, however, get an idea about the solutions by looking at this graphically. Let's plot both the left-hand side and the right-hand side of the equation as a function of e. That looks like this. The left-hand side looks like this. Actually, this is the right-hand side. The left-hand side looks like this. The equality requires that the left-hand side and the right-hand side are equal. This corresponds to the intersections of the two curves. These gives the energies of the stationary states. Let's sketch these energies in the box. We start with the lowest energy, then with the next one, then with the third one, then with the fourth one. We can label them with the quantum number n. N equals 1, 2, 3, and 4. We note a few things. First, there is only a finite number of bound stationary states, 4 in this case. This makes sense, since once the energy gets above V0, the particle escapes. Second, the energy levels are spaced similar to the infinitely deep box, with the spacing between adjacent levels increasing with increasing energy. How do the wave functions look like? Let's sketch them. Here's the ground state wave function. 0 out here, almost half a wave within the box, and then a decaying exponential outside in the right region. This is for n equals 1. For n equals 2, we get almost 2 half waves and a decaying exponential on the right hand side. N equals 2. For n equals 3, we get 3 half waves, or almost 3 half waves, followed on the right hand side by a decaying exponential again. N equals 3. Within the box, the wave functions are oscillating and look similar to the ones in the particle in the box with infinite walls. At the right boundary, the wave functions do not go to zero, but transition smoothly into decaying exponentials in the right region. This is remarkable. It means that there is a finite probability of finding the particle in the right region, even though the particle energy E is smaller than the potential V of the bound state. Classically, this would be impossible, since the particle has insufficient energy to overcome the potential energy barrier. For a quantum particle it is possible. It can penetrate into the classically forbidden region. What is the penetration depth, or the decay length, of this wave function? The penetration depth tells us how far the particle penetrates into the classically forbidden region. It's given by 1 over uppercase Kr, which is h bar divided by the square root of 2m times v0 minus e. Clearly, the penetration depth depends on the particle's properties. First, it's inversely proportional to the square root of the mass. That means light particles penetrate deeper than heavy particles. For example, electrons penetrate deepest, protons less deeply, and finally copper nuclei, for example, very little. Second, it's inversely proportional to the difference between the particle energy and the energy of the barrier, which is this term here. Particles with high energy close to the potential barrier give a small term here and therefore penetrate deeper than those with less energy, where this difference is larger. If the particle energy matches the barrier energy, this is zero. The decay length becomes infinity and means that the particle is not bound anymore and can escape.